What I have here is an FW Bell Model 5080 GaussMeter. It's a device for measuring the strength of magnetic fields. You can use it to measure the strength of a magnet or to determine what polarity the magnetic field is. I've got this here because somebody plugged into the power supply inlet here an unregulated wall wart that put in too much voltage into here, and it let the smoke out of some components. So I'm going to have a look at it and see if I can fix this thing. So let's pull the cover off and have a look inside first of all. So two 9-volt batteries go inside that cover and they connect to these two pins here, or these two spring clips here. Let's see if I can reduce that glare a little bit. There we go. Can we get in this close to focus it? So it's microprocessor operated, which is this device here. It's an 8051 compatible microprocessor or microcontroller. It's an 80C320 is the model number. It's a Maxim part. This would be the memory. It uses external memory. This is an older product here, and the microcontroller or microprocessor is what it actually is. Uses external memory. There's no memory inside it. In fact, there's very few peripherals inside the device. There's a couple of clocks and timers and watchdog timer, etc., but nothing like a PIC microcontroller or an Atmel AT Mega microcontroller would actually have in it. And here is an 8255 device. This is a parallel port. You run it off the microcontroller and allows probably, I think it's to run the serial port here. They bit bang it. Now, you probably can't see it too clearly. I'll get a light over there. In this corner here next to the power switch, you have a capacitor here that's been blown up. And that's what happened when the power was turned on. This capacitor blew up. It didn't have the voltage rating probably. And so I'm going to look through this thing and figure out if it's actually been damaged permanently or if it just blew up a capacitor and a few other parts. So let's flip this thing over and have a look at the other side. As you can see, there's more surface mount parts on the bottom. It's possible it was done by wave soldering. I would imagine the surface mount parts on the top here were done in a conventional way with an oven, and pick and place on the solder paste, and then this run through an oven, and then the through-hole parts put on, or maybe that would be these parts put on again after the first surface mount parts were put on, and these are held in by little dots of glue, and then the board was flipped back over again, and the through-hole parts were put on. And then this whole process, or the whole thing, run through a wave solder process to solder these on, as well as all the surface mount or the through-hole parts. But anyways, looking at the parts on the board here, we've got this device here. It's an ADC 1204. It's a 12-bit 216 kilohertz kilosamples per second ADC, analog to digital controller, or analog to digital converter. And this device here is the LCD driver for the display here. The microprocessor on this side would be talking to this controller here to put characters and whatever on the liquid crystal display. So that's basically all it. There's a lot of analog chips on this side through here. This is a digital to analog converter over here. I'm not sure how this board actually works. The probes that it uses are Hall effect sensor probes, and they plug into here. So there's a lot of analog circuitry here to measure those probes and get a value for the magnetic field strength. And this device over here is, I believe, a gate array, like a programmable logic device, which is just a whole bunch of logic gates inside it, and it can be programmed to perform certain functions. And I'm not sure what it's doing. It might have something to do with the serial port, or as this might have something to do with the serial port too, I'm not sure. So that's about it for this device. It doesn't work. I've tried it. It doesn't turn on. The two 9-volt batteries sit one there and one here. And when I took it apart, the battery that was sitting in here was actually warm. And I measured the voltage on it, and it's nearly dead. So there's some current being drawn. And even when the switch, this is the power switch, even when the switch is in the off position, there still seems to be some current drawn. And my guess is that this capacitor here is sitting across the power supply, and it's now damaged. It could possibly be shorted. And I'm going to take that off and see what happens to the rest of the circuit. So I removed that capacitor, and I've plugged in an external power source here, which is set to exactly 12 volts, or just slightly under, 11.99. And I'm going to probe the circuit to see where the voltage gets to. So this is the ground. I'm just going to leave that probe connected to there. And this is the capacitor that blew up. And with the power on, we get 12 volts on there. So that capacitor had been rated, I don't know, 10 volts or 12 volts. I think what ended up coming in here through the unregulated wall adapter was something around 16 or 17 volts, or even 18 volts. So it may have been more than what this was rated at, although 12 volts doesn't seem right. Anyways, looking through here, if I flip the board over, I can see we've got a device here. Put the ground back on again. This is a switching regulator, and on the other side of the board is an inductor that this works with. And pin 6 is the input, and it has 12 volts on it, unless the switch got turned off. There we go, 12 volts on the input. This is the output, pin 1. It should be 5 volts, and I'm getting nothing out of there. So I'm thinking that this guy got hit as well. It's rated to a maximum of about 13.5 volts. So if 18 volts came in through here and got to this point, I'm sure it damaged that switching regulator. And that's about as far as I can go for troubleshooting this without starting to replace some components. So the next thing to do would be to buy another regulator here and change it. Now I want to verify that nothing else downstream of this switching regulator here has been damaged. I'm going to remove the regulator, and there's a pin or a via right there. That's the 5 volt bus for the whole Gauss meter. And so what I'll do is remove this chip and then solder a piece of wire to that and apply 5 volts to this board and see if it actually runs. So now I've attached a wire to that point. It's actually a test point. It turns out you can see it on the top of the circuit board here. I ran it through and soldered it. So that's the 5 volt supply. Got a ground connection there and the 5 volt power here. Let's see what happens. There we go. Looks like it works. Well, there's no probe plugged into it, so that's probably why it's not happy. Let's go and get a probe and plug it in and see what it does. So I've plugged a probe in, and I just show you what a probe looks like. It's looks like just a stir stick for a coffee. But in the end here is a Hall effect device, and the wires for it run down the probe and into the cable here and into the device, into the meter. And the Hall effect device just measures the effect of a magnetic field on an electric current. Basically, it's a silicon chip, or I think it's silicon chip. You put a bias across one direction of it and measure the voltage across the other direction, 90 degrees to it, and then put the chip into a magnetic field, and the voltage that you measure across it will be dependent on the direction and the intensity of the magnetic field that you're measuring. So that's how a Hall effect device works. Now, let's just do this again. power it up and see if it works. Yeah, the ground connection slipped off here. That's what was going on. One more time. There we go. And there we go. Yeah, let's see if we've got, have to get a magnet and try it out. But it does appear to be working, and the power supply, or the damage from the overvoltage, only went as far as that regulator. And if I get a new regulator, solder it in, it should work just fine. Now let's get a magnet and see what happens here. So I've got a little magnet here. Let's bring the probe close to the magnet. No, definitely it changes. Yeah. Cool. So that's how it works. So I just zeroed the meter, and we're getting more accurate readings. Now if I bring the probe close to the magnet, you can see how it's increasing. And it shows a negative sign here. If I were to flip the probe over and do the same the other way, you can see there's no longer a negative sign. I can overrange this quite easily as well. It goes up to 299 or 300 Gauss. That's it. Anyways, this is the inner workings of a FW Bell GaussMeter. And hopefully when I get the new switching regulator and soldered in properly, the meter will work again off the battery or off of external power from this point here. Anyways, hope you enjoyed this quick little look inside a GaussMeter. So here we are again, taking another look at this GaussMeter. It's a couple of days later, and I've now got the parts to fix it. The switching regulator right here. But I had another look at it and started looking up some of the parts on the board, and got some better ideas of what all these parts are. This is indeed the analog section through here, and I looked up these parts here. They are they're ADG1 or 412, and what they are analog switches, basically just switches that allow the microprocessor to redirect the signals around the board to different parts of the board. This Gauss meter has a number of different functions. These devices here are most of them are some of them are op amps, and some of them are digital potentiometers. So they allow a variable voltage or a variable resistance to be produced, again under the control of the microcontroller or the microprocessor. What else do we have here? This chip here is a E squared. So it's what E squared stands for is electrically erasable programmable read-only memory, EEPROM. And it stores 4K bytes of data, and it's permanent storage, so it's retained when the power is turned off. So I imagine some calibration data is probably stored in this thing. I talked a little bit about this guy before. It's an expandable I/O port. I'm not sure what they're using this for. I thought it had something to do with the serial port, but it doesn't. Actually, if I flip the board over and I look at this device here, this chip here, and this is the serial port driver for the serial port here. And this chip that I originally thought might have been a programmable logic array isn't actually. It's the RAM for the microcontroller. I don't know why they put it way out over here, so far away from the microcontroller, but that's what it is. It's a 32K byte RAM. Remember I talked about the microprocessor here. It did not have any memory inside it. It has to access memory external to it, which is this chip here, which is the EEPROM that stores the software, the program, and the RAM chip here, which is used for variable storage, and when it's doing all its calculations and where to store numbers and other information temporarily. So that's about all that I was able to find out looking at some of these other chips. when I started looking closer at it, I found there was two diodes here. They looked both like this one, but the one that was sitting here ended up and I had to replace it because it had a little volcano in the middle of it. It looked like it received some high voltage and burned out. And when I investigated the circuit more thoroughly, I found out that these two diodes are connected to the two 9-volt batteries that plug into here. Essentially, these batteries are in parallel and connected up to the main power bus, which is actually the center pin of this barrel jack. And it allows the two batteries to run in parallel without being charged up when you plug in a 12-volt power source into this barrel jack here. And they all combine together onto one trace right here, which ends up going through the power switch into the switching regulator, which is going to go here, the new one that I'm going to put in here. So I think I've fixed every component that's been damaged. I put in a new capacitor here, which I managed to find in my junk box, and then I had to buy the switching regulator here. And a little bit about the switching regulator. What it does is it takes the higher voltage of, say, 12 volts or 9 volts from the batteries, and it drops it down to 5 volts, which runs the rest of the board. And the 5 volt supply for the rest of the board has to be fairly accurate and has to be constant. It can't be varying very much. Whereas the battery voltage, over time the batteries start to lose their charge, so the voltage on the battery terminals goes down, but the switching regulator will keep the 5 volt supply constant. So I'm going to replace this chip off camera because it is too hard to work with underneath the camera here. And then we'll start the camera up again and have a look at the results of replacing the chip. Hopefully the board will work properly. Okay, now I've soldered the regulator in place down here, and I'm just going to try it out. So I've got a 9-volt battery, and I'm going to hook it up to the battery connectors. So let's try this one. That's the plus terminal. That's the plus terminal. So we'll hook it up here. Oh, make sure it's turned on, and nothing. Well, like I said, there's two batteries in parallel. They're independent. So let's try this one. Ah, there we go. Okay, great, that worked. No probe, but that's fine. This thing is working. I wonder what happened with this side here. So let's flip the board over. This is the positive terminal from that battery. Let's just trace it back all the way around. So it's going to this other diode that I thought was okay. This is the one I replaced, and it seems to work fine. So now I'm going to replace this diode with another one. And again, I'll do that off camera because it's a bit too awkward doing it under the camera. I can do that in a minute. Let's hook up a 12 volt supply. Here's a barrel jack hooked up to my power supply, and I'll just bring my meter in here and see what it's reading just to make sure. Alright, 11.99 is good enough. Turn it off, plug it in. No smoke. There we go. Great. It's working on the 12 volts. So just that one diode has to be replaced. That shouldn't be too hard to do. Okay, now I've replaced that diode. Let's try it again. Turn it on. So I know this side worked. And this side. Ah, there we go. Great. I'll just show you what I did with the diode here. How clear this is. Now, these were two surface mount diodes, and I tested them. Well, this one here was obvious because I could see a hole burned in it. Something had gone wrong with it, so I replaced it right away. This one here, which I thought was good, I tested it with my my fluke meter, which has a diode test function on it, and the reading I was getting didn't seem quite right, but I thought it was okay, so I left it. So I guess the diode actually was wrong, or was damaged by the overvoltage. I don't have any surface mount diodes in my junk box, and I forgot to order them when I ordered the switching regulator. But it doesn't matter. I just took a couple of small signal diodes, 1N41/48, bent the leads around and cut them off, and then soldered them directly to the pads of the original diodes. And that's doing the job just fine. So here is a fixed Gauss meter. I hope you guys enjoyed the little teardown, the mini teardown here, and the repair. And perhaps I will find some more equipment to do the same thing with. This was given to me a couple of days ago by my someone I'm contracting to, and they wanted it fixed because it. I looked on eBay, and one of these used goes for about $1,300. So I could understand why they wanted it fixed. It was a lot cheaper to fix it than to buy a new one. Anyways, I've got to go because they want this back and they need it for work. Hope you enjoyed this video. See you around.